once you set up the apparatus, because everybody's is different, every team's is different, take a photo, draw a sketch, label it, right? Because it may not be obvious what part is what anymore. So make sure you basically put that in, especially that whole elaborate scaffolding you set up, right? Everybody's going to use the same WDSS, I know. Everybody's going to use the same rotodine wheel, I know this. But everything else is pretty much up to your imagination, right? So you got to label stuff. All right. So relevant equations. This is where basically we're going to actually try to predict what we're going to do. Okay, so it says here, let's basically draw free body diagrams for the week. Okay, so got the rotodine wheel here. Got WDSS over here. Got a hanging mass over here. Pretty simple system. All right, let's draw free body diagrams for each of these. First of all, unlike the bricklayer problem, how many objects are there now? There are 3, right? There's the hanging mass, WDSS, and what? Right, the wheel is no longer massless. Gotta worry about that. Okay, we know how to do these, right? This is easy. This is literally one force. Again, try not to, let's say have a weight force. It's the weight force, thanks. Okay, so I'm going to call it weight WDSS. Countering that weight force is what? Tension. I'm going to call this tension WDSS. All right. Okay, hanging mass, same thing, right? Weight, mass, tension on the hanging mass. And here is a big difference. Remember last time with the bricklayer, we assumed what was true about the two tensions. They're equal, right? There's no reason to believe they're not, right? Because the rope is taut, that means that they're going to be the same tug on each side. Now, do we assume, with the wheel being massless, or not being massless, that the tensions are the same? No, no longer assume that. Because, and you're saying, why? Isn't the rope still taut? Yeah, the rope is still taut. But where is some of the tension being taken up? Right, in the movement of the wheel, you'll see that, right? So, here, big difference is T WDSS not equals. We can't make that assumption. So all of a sudden, how many unknowns do we have? All 4, right? Yeah, some of them are calculable. Because are you going to measure the weight of the WDSS? Are you going to measure the weight of the hanging mass? Sure, of course you are. So mg gets you W. That's easy. The fact is that again, we have 4 different letters. Okay. Another new part is this. How do we draw the free body diagram of the wheel? First of all, where do the forces emanate from? Where do the forces go? Where are the forces acting? You got a whole big wheel. Where are they? There. Where would be a logical spot? Right. Where is that wheel contacting anything else? And you all built it so that it was contacting along what? And the axis, right? The axis of rotation, right? Literally the axle, correct? So that's a good place to put where all the forces emanate from, because that's where the outside wall touches the wheel, right? At the axle. Okay. So draw the free body diagram here. What are the forces that are acting on this wheel? The wheel have a mass. Therefore, it has a weight. I'm going to call that W wheel. Okay. Now, obviously, that wheel is not dropping precipitously, so there must be a countering force, right? Yeah, it's going to be the normal force, not the tension, right? Because the rope isn't acting on the mass per se, but the fact that whatever you're holding that axle in place with is pushing up on the the axle, that's going to be the other force. So there's a normal force. All right. Are there any other forces acting on any of the other bodies? There's not a normal force on the string. Are we worrying about the string? No. Yeah, if we have given the string mass, then you'd be correct. But we're going to assume the string is massless because, goodness, 3 objects is hard enough to keep track of, right? It turns out, is the string's mass significant compared to, say, even the WDSS's mass? Well, no, it's not. It's certainly not as much as the wheel, right? Okay, so is everybody okay with that? All right, so now it says here, set up the coordinate axis. So, all right, how are we going to do the coordinate axis? Last time when we did the bricklayer, how did we do the coordinate axis? How many axes did we need? Okay, so let's start off with that. So let's say over here on the WDSS side, I make positive and negative that. Okay, that means for the hanging mass on this side, what does the coordinate axis look like? That whole stretch out thing. Yeah, it's going to be upside down. Is everybody okay with that? Right, and we're stretching out the whole thing, right? Long axis. And what about the axle? What about the heel? Okay. It turns out it doesn't matter. We could use this one or this one. I'll just use this one just because. So the thing that the rotation is happening with in these kind of systems doesn't technically matter. But nevertheless, how many axes? Still just. Okay, we did that. Yay. Finally, set up the sum of all forces equation for the WDSS. All right, let's do that. Okay, so for the sum of all forces for the WDSS, I think this is pretty straightforward. Okay. Again, we're not going to do vectors, right? So we're going to use signs instead of vector notation. So in the positive direction is the tension. In the negative direction is the weight. But we just know that the weight is what? You already said it. You already said it. Big for P, right? Mass of the WDSS. P, right? All right. Do we need to do any of the other ones? And the hanging mass. Okay, so let's do the hanging mass. It's just the opposite, right? It's W hanging minus T hanging. This is just M hang. All right. And then I'm not going to worry about the torque one, but let's do the whole this is equal to some second law thing, right? So what are your choices? 0 or on the right side equals 0 or. So which one do you think works here for both of these guys? First of all, if it's 0, have you done anything that helps with the lab? This is an emotion technically. No, you've got a balance, which kudos to you. You managed to balance to do things, yay! But it's not really going to help because you want an acceleration and potential. So, one. Okay, sure. So this one is going to be MWDSS. Okay, this is going to be M. And do I have to distinguish the A's? Are the A's the same or are the A's different? The tensions are different, right? But are the A's different? Have to be the same. Why? Yeah, they connect by the same rope, right? Yeah. And the rope doesn't change length. Right? So the point is that what one does, the other one better do. So it's not true for the tensions, but it is true for the accelerations. So fortunately, we didn't introduce too many more new variables, right? Just A. But technically, this is one unknown. We know these two. We don't know this one. We don't know this one, right? So that's 3 unknowns and only 2. Not a solvable system. There's a whole family of answers, right? Okay. So what about the wheel? Should we actually draw the free body, or should we draw the sum of all forces for the wheel? Or will that not tell us anything useful? That's not useful at all, right? Literally, the wheel isn't moving, so the second law side is 0 or ma? 0. So we get n minus w wheel equals 0, or that the normal force is equal to the mass of the wheel times g. That's not super helpful, right? It's very true, but it's not going to get us anywhere getting A, right? So it's so we're not going to worry about this guy here. It's not going to be helpful, right? Instead, our third equation that connects the tension and the accelerations is going to come from the sum of all torques equation. It turns out that the torque is really useful because it allows you to not just connect the acceleration and the tension, but it's basically what's called one of the equations of stability. So when many of you are going to do this, how many? Well, actually, I should say the poll. How many of you are going to take statics, either now or taking it next quarter? All right.
It's not offered next quarter.
It's not offered next quarter. Okay, what about in the summer then?
Oh, it's only in the fall.
Only in the fall?
Yeah.
We suck. Okay. How many of you are going to take engineering statics at some point? Anywhere, not even here. Yeah, a lot of you are. Okay, that's a good thing. That's a good thing because it's even required for computer science, right? At least you know. So the point is that basically that's when chapter, I believe, 12 comes in super handy. Either 11 or 12. It has the equations of stability. Most of them are the sum of all forces. Right? You draw a free body diagram, do the sum of all forces, and if you set it to 0 or ma, you're good to go. The other one is always going to be the sum of all torques. And it turns out that a super important thing is that any rotational motion, right? So how do we calculate torques? We're going to have to do this, right? Where are there torques? Where's the only place where there's torques? Probably on the wheel, right? So if you want to put tau wheel here, that's fine. I'm not going to write here because I want to keep it as generic as possible. But going back, actually, I'll redraw it because it's easier. Redrawing it, just the wheel part. I've got the axle here around which everything spins. Where are there forces that are acting not towards the center? In other words, not at the axle. The normal force is the weight force acts at the axle, right? Yeah, we neglected a couple of very important forces there, right? So specifically, if these two tensions aren't the same, can they be part of a third law pair, which is how we always justify something, right? They're not the same. Is it a third law pair? Yeah, which part of equal and opposite don't you get, right? Okay, yeah, they're not equal, okay? All right, so obviously they're part of different third law pairs now. So where is the equal when opposite to this arrow here? Arrow on the WSS. Yeah. It's where this rope touches the wheel, right? You agree that that contact point, the rope is going to exert a force on the wheel. Okay. Go ahead. Now that's a great question, but it's the tension, right? So it has to be along the rope or whatever, right? So in other words, in our picture here, if it's contacting right here, we're not worrying about the contacts up here, right? This is the first point it's contacting. We'll assume all the force is concentrated there. Which way is the tension pointing? Literally. Right? Yeah. So we have another TWESS, because that's the third law pair, right? Everybody okay with this idea? Weird, right? But we need to do that because every arrow up there better have a third law counterpart. The only exception is W's, right? W's basically have a third law pair where? Down somewhere at the center of the arrow. All right? Where's there one other arrow we were missing? Where's the third law paired to this hanging? Remember, it's not going to be WDSS, right? Where is that other part of the rope contacting? Yeah, exactly on the other side, right? 3 o'clock position, right? Okay. So right here, so I can draw T hang, pointing downwards, then there's your third law pair. So whenever you have a pulley or any system like that, remember, whatever tension is being exerted by the 2 masses on each side, the third law pair is directly above it, pointing down. If you need an empirical rule, there's your empirical rule. But of course, there's a deeper underlying theoretical reason for it, which is literally I need third law pairs. All right, so is everybody okay with that? Kind of weird. So, going back to this picture then, if I draw those forces, accurately. All right. We agree that these are not acting at the center of mass, on the center of mass. They're not acting on the center of mass. You notice that the normal force and the weight force of the wheel are acting on the center of mass, right? So the point is, the only 2 forces that will exert a torque are these 2. Okay with that? So even though there are 4 forces total acting on the wheel, only 2 of them are going to matter for the torque. The ones that are not on the center. All right. So what's the one other number that we need in order to be able to calculate the torque for either thing? Yeah, we need the radius vector. Okay. What does the radius vector look like on this picture? Literally, always pointing outwards, right? So this is the radius WDSS. This is the radius, the hanging mass. Fortunately for us, are they the same? Better be its own wheel, otherwise it's a really dumb wheel, right? Okay, so the point is that we now have everything we need. Torque then, recall from your cheat sheet, torque is R what F? What's the operation between R and F? Cross product. Okay, so we're going to try to do this without having to make vectors. Fortunately for us, with both of these cross products, according to the right-hand rule, which way is your thumb pointing when you cross R into F? Either out of the board or into the board, right? So we can use signs, right? Let's say out of the board is positive and into the board is negative. How about that? So I'll write that over to the side here. So that one is positive, pointing out towards you. That one is negative. Remember, into. Hear that so far? Okay, deep breath. So let's do the calculation. So the sum of all torques is going to be R cross into this force. So remember, when you do the cross product, do the mental thing, right? Move this arrow over to here so that they're tail to tail. And then how do you use the right hand? Vector, which vector are your fingers going to curl? Now, first vector to second vector, right? First vector to second vector, right? So, is this torque going to be positive or negative? Positive, great, because I didn't leave myself enough space for minus sign there, right? So, great. And it's just going to be R times T, WDSS. Okay, and you remember there's one other part to the cross product's magnitude. It's the first vector times the second vector times something tricky, sine theta. Okay, what's theta between R and T? Increase. Everybody agree that this is a right angle? Okay, that's why we don't have to worry about the side turn. Yay! Okay. I will give you a task, I think it's task 28, where that's not true. So be careful. We're going to get lulled into the sense that it's just the 2 things multiplied together. No, not always. Be careful. It's the sine of 90 that we're always ignoring. I'll put it here once so that you know that that's why we're not dealing with it. Okay. What about the other one? About this? Do the cross product. Now, basically, I'm crossing this way, right? The sign, S-I-G-N, on this is what? It's going to be negative R times F, which in this case is T hang. You agree that the angle is 90 degrees again? Yep. Right angle there. Sine of 90 degrees, which we can ignore. All right. Any other things that have torques? Okay. So now there's the third law or second law equivalent. But this is a torque, right? So the choices can be 0 or what's the rotational equivalent? Look at the cheat sheet again. What's the rotational equivalent for MA? Both letters are going to change. Mass is replaced by I, the moment of inertia, and A is changed to fish or alpha. Technically speaking, right? Okay, which is the angular acceleration. So everybody okay with this? Right, and that's how you do torques. So to get the first and second law version of the free body diagram, sum of all forces equation, that's what you do. All right. So it seems that we've introduced another variable, right? We got an alpha, this angular acceleration, which wasn't up there before. Clearly, these two are still unknowns, which is great. But the whole point of this was to get a third variable that was the same as the three variables up there, namely having A. No, this is where your cheat sheet comes in handy. Because alpha is literally equal to what with A? Now, look over on the right column, up by where we were talking about angular acceleration. You got it. Does everybody have on their sheet some version of that? Actually, that's incorrect, right? The other way around, right? Better be A over R, right? Yeah. Because if you think about the units, think about how this has to work. This is going to be, as we saw with the mouth guard thing, radians per second squared. That is, say, no units over second squared, right? Meters per second squared, and unless I divide by meters, units are not going to work. Everybody okay with that? Okay. So of course, then I'm just going to replace that into here, and it's going to be I A over R. Just said, hold on. You introduced yet another letter, this I. Actually, I did it. Because can the moment of inertia be calculated? Absolutely. In fact, if you go back into the cabinets here, I'll show this to you on the screen in a second. There's actually a manual, an operating manual. This. Operating instructions. And one of the great things about operating instructions is they have all the specs on this device that we've got here. So, the thing that I'm going to show you then are some numbers you may want to jot down. Sorry, it's going to take a second for this thing to up. My apologies. Go. Okay, so show up. Yeah, I did. Hey, how about that? Okay. Let's see. Center this and blow it up a bit, and then turn on the lights. Okay. So notice it has a lot of data that might be needing. Like for instance, how far away those screw-in mass holes are from the axle. Okay, so those are good numbers. Some of them are 2 sig fig, which is unfortunate, but there you go. I don't think this experiment is going to be good to more than about 2 sig figs. By the way, there's a typo. Does anybody notice the typo in these 5 numbers? Go with the second screw holes number. Yeah, it's inside the first, right, which doesn't make sense. I think they stuck an extra 0 in. It's actually that, right? So 7.5 centimeters, 10 centimeters, 12.5 centimeters, and so on. So make note of that typo. I'm going to put a little cross through it since I haven't before, so I might as well put it down. Okay. Other things you might want to know are the wheel radius at the inner rim. Okay, that's good. And then there's this other weird number. Oh, yeah, it also has the mass of the wheel too, just the rotating element. So it's the part that you stuck on there, right? It doesn't count the base, but you didn't use the base. Or the base isn't rotating anyway, right? So the wheel itself weighs 1.41 kilograms, and to give you an uncertainty. By the way, what do you think the uncertainty is in these guys down here? Clearly, they're trying to get you to do what? Plus or minus? Yeah, I mean, even though some of these are 2 sig figs, I'm going to give you permission to make this 100 and 150, and then make it plus or minus a millimeter, right? 0.001 meters. Because they're not going to give it to you that precisely unless they knew. And they're machined, right? So it's not like the CNC router or whatever they used to make those holes with. Basically, didn't know how to do that, right? All right, so the other number is this radius of gyration, 0.14 plus or minus a tenth of a meter. And you're going, what the heck is a radius of gyration? Well, you notice the wheel is somewhat irregularly shaped. I mean, it's not a perfect cylinder, it's not a disc, right? All that kind of stuff. And some of you have looked ahead. In chapter 9, there's this awesome table that actually shows the moment of inertia of a lot of these different bodies, right? So let me just show you that. I think it's at the end of chapter summary. There we go. Nope, not quite at the end of chapter summary. It's probably there we go. This is on page 286 of the 15th edition. But it's the moments of inertia of a bunch of different regular shapes, like cylinders, like rods, that kind of stuff, right? And notice that where the axis is makes a big difference. And I'm hoping that these are intuitive to you. In what sense? What do you think the moment of inertia is? What is literally the definition of mass? That which does what to a force? Yeah, often the word that's used is resists force. So in other words, you know that there's a mass because my force isn't going unimpeded, right? It's something is fighting. Moment of inertia is the same thing. The word inertia literally means not moving, right? It's to basically get that thing to move. So when you spin a rod around the middle, and when you spin the same rod around its end, which one is harder to do? Right, the end. Check out what the moment of inertia is. Is it bigger or smaller than the moment of inertia for around the middle? Bigger, right? It's 1/3 versus 1/12, right? So in other words, it takes 4 times as much force to get the same kind of motion doing this as I do just simply doing this. Why? Because there are parts of this rod that are not bigger, but further, right, from the center. That whole lever arm thing, right? So I hope these numbers are somewhat intuitive to you. But I will illustrate this with another point here. Somebody grab one of the wide boards, in fact, that widest board that's over by the corner of the room there, and set it up on one of these tables. Let me turn the light so you guys can see it. So Let's set it up here. All right. Help me. All right. All right. Actually, Mike, can you help me? Let's do steam. So let's do it like from here. We're gonna do a race. Would you confirm for me? Roughly the same. Roughly the same. Okay. Okay. Roughly the same. Okay. All right. So my lovely assistant, Mike, is basically holding up that board. And the point is that I'm going to roll these two things down the board. Obviously, they're only rolling because there's a force of the weight dragging them down, right? Or if you want, I'll call it the force of gravity dragging them down, okay? The point is, according to your linear stuff, if I just did it this way without them rolling, just sliding, which one would hit the bottom first? Okay, let's go back to Neil Armstrong and the moon. Penny and the feather, quite a bit different, right? He drops them, which one hits the surface of the moon first? Okay, so let me do this again. I drop these from the same, or I slide them from the same height, which one hits the ground first? They're the same. Yeah, it doesn't matter about the weight, right? It doesn't even matter about the distribution. The point is that any dropped object falls the same rate, right? Okay. All right, now I'm going to roll them. Do you think that makes any difference? You just told me they're supposed to hit the ground at the same time, right? What do you think? Which one's going to win? Okay. You see what the cases we're talking about here are? F and G, the solid cylinder versus the thin-walled cylinder. Okay, a hollow one. Okay, how many of you want this guy to win? All right, how many of you got the solid one? Okay, all right. So keep in mind, which one has more moment of inertia between F and G? Yeah, the hollow one does. And again, it's because there's more heavy things on the outside compared to this guy, right? Let's see what happens. Then the drum will roll it now. You ready? So it was slight, but did you notice in one?
Hollow one.
So it was a hollow. Kind of basically, like we lowered down a little. Yeah, let's see if we can basically drag it out a little bit here. Okay, all right. I'm gonna put them side by side. Oh, that one was a little bit more clear, wasn't it? Let's just see if it was an artifact of that angle. Like we lowered it a little bit further. Thanks. Hopefully they'll roll still. Okay. Whoa, even with a head start, the solid one won. Thanks, Mike. Okay, so the point is, the solid cylinder won. Why? Yeah, there's less mass resisting the motion, right? 1/2 versus 1, right? Okay. So the point is that, yeah, things with less moment of inertia are easier to move. Not a big shock. All right. So the point that I want to make with this then is we can't unfortunately use, I mean, what does the wheel look like the most? The Rotodyne wheel you guys are going to use. What does that look like the most? I mean, I was thinking kind of a solid cylinder, right? Or maybe a hollow cylinder or thin-walled cylinder, right? But it's really even hard to model it that way, right? Because it's got those spokes and all this kind of stuff, right? So it makes it really hard. So fortunately, these guys were smart and said, you know what? That's really going to be hard to calculate for you guys. So why don't you go ahead and use, let's see, there it is. That formula, I equals mr squared. And says the simplest moment of inertia equation is for a hoop of radius r, mass m, rotating about its center. The formula is this. Okay, and they said, yeah, we noticed that that thing isn't the same shape, but Formula 3 is used as a convenient method of defining the radius of gyration. And so they're basically saying, hey, look, um, so we can use that formula. Let's just basically make we'll use that formula. We'll just use the radius of gyration instead of the thing. And so that's where they came up with that number, which I just now noticed is a little bit different than this number that they give, but I think this one's more accurate. So go ahead and use this one. So we're literally going to use I equals mr squared, m wheel, r gyration squared in order to calculate. Okay, this is a long way of explaining. Do we know I? Yeah, we can totally calculate I, right? No problem with that. So what literally are our unknowns? Right, acceleration, circle them, and do we know the tensions necessarily? Nope. Okay, so these two are the other unknowns. We have three equations, two unknowns, or three unknowns. Is it a determinable system? Of course. Okay, so the rest of this is going to be algebra. So, Mike, if you want to switch over to this camera over to here. Okay, great, thanks. And I just lost my they're all over here. Okay, this is going to be a bunch of algebra. All right. So there's numerous ways to approach this. I'm just going to start with the torque equation, right? So I have, and by the way, is little r the same as r gyration? Please say no. What's little r on my chart of numbers here? Now that's the big R. Yeah, 0.20, where the string literally is on the outer rim, right? Remember, that's where we measured that red arrow, right? So be careful about that. Is there an uncertainty on that? Of course there is. It's going to be plus or minus. Yeah, and we could probably throw another zero on it because unlike the radius of gyration, which is sort of making up, right? I can see putting a big uncertainty on that. The radius, the outer rim radius, is not a hard thing to measure, right? So I'd say it was 0.200 plus or minus 0.001, right? In other words, a millimeter. We should be able to know it to that. Is everybody okay with that? All right, let's do the algebra then. So we're going to start off with RTWDSS minus RT hanging is equal to all that stuff, which is literally what? MR squared. So I'm just going to keep as I because we know how to calculate that, right? So that's easy. I, A over R, little r, right? Okay. So one thing that we can do then is start subbing in other things, right? Like for instance, what equations do we want to ultimately end up with? Something equals. What do we want to end up with? We want two things, right? Not in units, just literally what letters do we want to know? A, okay, equals, and what's the other one? What's what's the goal of the left? Yeah, tension, right? Which tension? No, because there's only one you can measure and check. Yeah, the WDSS, right? That's the reason you're hanging the WDSS on the thing, right? Is so you can check whether or not you called the shot. So we want to shoot for this one and this one. Okay, so let's see if we can do that. All right. Obviously, let's get rid of hanging mass then, right? The T hanging mass, right? Because that's useless. So T hang up there is equal to move things around, M WDSS, let's see, minus, no. Yeah, actually, I can just do it this way, right? G minus A, right? And that's legal, right? I swap T and M hang A, and then I just collected like terms. Everybody okay with that? I think I did that right. Did it? Oh, I'm looking at the wrong equation. Yeah, you're right. This is M hang. Better? Okay, are we good? All right. So, um, I put that into here, obviously. And so I get R TWDSS minus R times this mass of horrible letters here. G minus A equals IA over R. Okay. That's not so bad. I've literally got TWDSS in one thing only, right? So I'm just going to leave that here, move everything else to this side, and divide by R. Okay, so let's do that. I A over R plus R M hang G minus A all over R. I think I did that right. Okay, obviously the R's cancel here. They don't cancel here, so I can't do what I was thinking of doing, but I can still do this. 1 over A, 1, oh, sorry, IA over R squared, and then I can cancel the R's, M hang G minus A. Then I collect A's, and I get, I can pull, yeah, I don't know if it's worth it, okay, because you know what the next step is going to be. I now have an equation for TWDSS, right? Where am I going to stick it? In that top equation, right? Okay. So TWDSS is equal to, is it G minus A? I don't know. Let's look. So I've moved M hang A over to here, T hang over to here, right? Keeping all the signs. And so it's going to be M hang G minus M hang A. So it's G minus A, right?
Oh, I'm sorry. It's flipped.
Yes, because the axis. Good eye, though. It's good to check these things. All right, so the top equation, TWDSS equals, this one's going to be plus. So MWDSS G plus A, right? That's right. Yes. All right, so those two are equal. So we just basically, all right, here's the kind of horrible thing. Now that these are equal, the two right sides are equal. So let's just write out the whole horrible thing. So it's MWDSS G plus MWDSS-A. That's the easy left side. And then there's this horrible right side, IA over R squared plus M hang G minus M hang A. I guess that's not so bad, right? It's kind of terrible. All right, but now we collect all the A terms. Let's put them all on the, I don't know, left side. Okay, so we get MWDSS plus, minus I over R squared. Okay, minus, no, that's going to be plus M hang, all multiplied together to get A. Move all the other stuff on this side, so it's just going to be M hang G minus MWDSSG. We can collect the G's. So A is equal to that whole thing divided, so it's going to be G times M hang minus MWDSS all over this horrible thing in the parentheses, MWDSS plus M hang minus I over R squared. Easy peasy, right? Okay. But you notice, is this a lot different than the bricklayer equation that you got for the acceleration? A lot different? No. The top was the same. The bottom is the same except for this new term, right? So literally all the rotation adds is this little chunk here. Let's make sure the units work out. What are the units? Well, the masses are obvious, okay? The masses cancel these masses, and we have G, which is in terms of acceleration, right? So that's easy. Let's make sure the new guy doesn't screw things up. All right, what's the units of I? MR squared, right? So literally, kilogram what? Kilogram meter squared, right? MR squared, right? Okay. R squared is obviously meter squared. They cancel, and you end up with kilograms. So the new guy doesn't screw things up. Okay. So you notice what's going to happen to the acceleration now that I've got a minus I over r squared here. This number is going to do what to the denominator? Yeah, it's going to lower the denominator. These are positive numbers. This is going to be positive too, so this is going to lower the denominator, meaning that the acceleration overall is going to be what? Bigger. Okay. Interesting. Didn't expect that. All right. How do you get TWDSS? How do you get the attention on the WDSS? I got the acceleration now, right? Just feed it back into what? There, right? And we know everything else, right? I'm not going to write the whole thing out. I mean, it's pretty horrible, but I expect you to, so I will leave you to something to do. And the point is that you should be able to get a real world prediction for what you're going to get. Okay. All right. So let me go back to the lab. Okay. So there we go. It's finally the moment of inertia. I set all three equations equal to solve for the predicted tension and the predicted acceleration. Okay, so that was question one. Fortunately, the other questions aren't much. All right. So now that just running the wheel by itself is called the scenario one. In fact, I think I listed scenarios here. Scenario one is just the wheel and the counterweight. Scenario two is when you screw the 4 screw-on masses on each of the innermost holes that are on the wheel. Scenario 3 is when you take those same 4 and put them on the outermost hole of the spokes. Are you okay with that? All right, how does that change the moment of inertia, you think? Remember our little race that we had here. By putting any more masses on, what are we going to do? Increase or decrease the moment of inertia? Increase. And by putting them further out, I do further what? Further increase, okay? So in other words, the slowest acceleration you should get is scenario 1, nothing. Scenario 2, innermost. Scenario 3, outermost. Scenario 3, right, you got it. Okay, so let's see if your calculation bears that out. All right, so to do this final part then, what equation will allow you to calculate the moment of inertia of any given screw-on mass? Running out of space here, so I'll just carve out a little block here. Does somebody want to adjust the camera? Or am I on camera? All right. So with the screw-on mass, remember the scenario looks like this. I've got a wheel, and now I've got a screw-on mass on the innermost holes, these things. So the question is, how do these screw-on masses affect the overall inertia? Okay, so we know that I, according to this thing here, is m wheel plus or times r gyration squared. Okay, that's just this equation. How do you deal with point masses? So we're going to pretend that these cylinders are point masses. Why not, right? They're pretty compact. How do we basically determine what their contribution to the wheel's overall inertia is? Do you know the formula? Used it about a zillion times here. In fact, it's sort of self-referential on that. It'll be the mass of the screw-on wheel times what? Or screw-on mass times what? Yeah, how far it is away from the center. That's all it is. So literally, plus m of the screw-on mass times r of the hole. Remember, those are some of the numbers that were on this thing, right? So the outermost hole is probably good, or the innermost hole is going to be the 0.075, right? Okay. The point is then, how many of them do we have? How many spokes were there? Somebody in the back. Yeah, 4. Okay. So what's the only other factor I need to put on this guy? Tell me how many square masses there were? All the same distance away, right? All right, so that's how you're going to change I to adapt to scenario 1, or scenario 2, and scenario 3. Everybody okay with that? All right, so let's see if there's anything else to cover on task 24. Yeah, on this one, get the masses. And I think it's okay if they are all, one thing you want to do is to take off any tape that's on them when you weigh them, right? They should all pretty much weigh the same. I have 8 slots here. You only need 4 of them, right? And if the mass basically works out that they're fairly close, you can use one of the masses here instead of having to add all the separate ones up, okay? I have you measure the diameter here. Don't even worry about that because we're going to pretend they are what? What kind of mass? Extended or point? If we make them point masses, we don't have to worry about the diameter, right? So don't even worry about that. So the point is, you just want to get the mass and the radius, by the way, that should be squared, on the of the hole from the data sheet. 4. Okay, well, in fact, here's where you can copy it down, right? The data from the center. Again, then calculate the total moment of inertia 5. That's easy. All right. The gum expression for UI, which leads to the whole gum expression for UA and UT. Yeah, it's going to be horrible and messy. Let's not do it today because I've run out of board, right? Let's do this one on Monday. Okay. So why don't you go ahead and basically see if you can do this experiment now. All right, everybody know what to do?